Hey guys, welcome to another A-level further maths revision video. We're taking a look at some more core pure revision, and we're taking a look at the second year volumes of revolution. So we're not going to look at the parametric volumes of revolution or parametric curves, just introducing the trickier ideas here at first. So involving trigonometry, quotients, sometimes logarithms. So let's just take a look at what we've got here. We've got 3 questions. These questions are usually quite long, so hopefully it won't take too long, but let's have a look, see what we've got. So we've got this curve here with the equation y equals cos x times the square root of sine 2x. We've got a graph here, which is just, I guess, to kind of give you a bit of a visual aid, but it won't be particularly important. But we're asked to find the finite region enclosed by the curve and the x-axis, as demonstrated in this sketch here. Okay, it's rotated about the x-axis, and it forms a solid of revolution. So we want to find the volume. So y is equal to cos x root sine 2x. Okay. Well, if we want to find the volume of the solid, if it's rotated about the x-axis, what we require then is that v is equal to pi times the integral from a to b. So that would be our limits here. So in other words, 0 to pi over 2. So it's about the x-axis, it'd be y squared here. Okay. And obviously the variable that you're integrating here with respect to is x dx. Okay. Y squared, well, that'd just be cos x times root sine 2x. Cos x times root sine 2x squared. So if we write this out in full, this is pi times the integral from a to b. So a is 0, and then b is pi over 2 of y squared, and y is cos x times root sine 2x. So if you square that, that's going to give you cos squared x times sine 2x. Okay. So we need to now find the integral of this. So how would we do this? Well, this is a bit challenging to integrate at this point, but this is very common in this chapter. We're going to use some trig identities. So we've got the double angle formula for sine x here, sine 2x. So we can write sine 2x as 2 sine x cos x. And it makes it a little bit easier to integrate now. That's going to be pi times the integral from 0 to pi over 2 of, so if you times cos squared x by 2 sine x cos x, that's going to give us 2 cos cubed x sine x. Okay, dx. Don't forget your dx's. Okay, I can take this 2 out here using linearity. So what I've got here now is 2 pi times the integral from 0 to pi over 2 of cos cubed x sine x. Like so. Okay. So now we've just got to find this integral here. A nice way to do this is using substitution. So integrate using substitution. Integrate using substitution. So what am I going to substitute? Well, the bigger issue here is this cos cubed x. Okay. So if I say u is equal to cos x, obviously we need to find dx as well. So du by dx here, well, that'd be the differential of this here. So if you differentiate cos x, you get minus sine x. So in that case, then dx is going to be equal to du divided by minus sine x. Okay. Or in other words, it's minus 1 over sine x times du. So now we can kind of put all this together. So if I kind of just line it off over here, so we've got enough room to do it. So again, this is 2 pi. This is the integral 2 pi times 0 to pi over 2. So technically my limits are going to change here, but we'll discuss that in a second. Let's just write what this would be when we substitute it. So cos cubed x, so that's going to be u cubed. Then we've got the sine x here. And then dx is du over minus sine x. Like so. Okay. Notice these sine x's will just cancel. So what I get left here with now is this minus du. Essentially, but you can take this minus to the front here if you want. So what I've then got is 2 pi times the integral of minus u cubed du. Now, just a quick note on the limits here. You can change them if you want, and then just do the integration with the new limits, or you can perform the substitution, just forget about the limits for now, and then just make sure you substitute back in afterwards and keep the limits as they are. What I'll do is I'll just consider the new limits, and I'll also do it with the other limits as well, just so I've demonstrated both examples. So, if you consider the new limits here, well, you need to consider u equals cos x. So what is u when x is pi over 2? So that's going to give you 1. So you're going to get, sorry, that'll give you 0, and then cos x at 0, you're going to get, or cos 0 is going to give you 1. So your new limits will become 1 and 0. Okay? So, then with your new limits, so if you perform this integration now, this is just going to be 2 pi times, add 1 to the power divided by the new power, minus u to the 4 divided by 4 between 1 and 0. So essentially here now just substitute 1 in, substitute 0 in. You end up with minus 1 over 4 times that by 2 pi. That's one way of doing it. Or I could write this, so imagine there's no limits here, we'll just perform the integration. This would be 2 pi times, where u is cos x, so that's going to be minus cos x to the 4 divided by 4. And then your limits would be the original ones, okay, pi over 2 and 0. So if you're going to change it back to the original substitution here, make sure you stick with the original limits. If you're going to keep it in terms of your variable that you're substituting, so u, make sure you change your limits. So that's just one little thing to watch out for. But summing your limits either way here, you'll get the same answer. So what you get is 2 pi times 1 over 4 and 2 pi over 4. 2 pi over 4 is equal to pi over 2. Okay, so pi over 2, that's our volume there. So V is equal to pi over 2. So 6 marks for that. Like you can see, there's a lot of kind of little things you've got to watch out for in this chapter. So, you know, make sure you're confident with your integration. Make sure you're confident with Trig identities. Very, very important for this chapter. Okay, but let's take a look at the next one. This next one's slightly different. We've got this quotient here, 1 over 2y plus 1. And we're given the volume this time. We want to find a limit. So, let's see if we can do this. So, x is equal to 1 over 2y plus 1. And we know the volume is pi over 10. So we just want to find the upper limit here. Well, what is it rotated about? So it's rotated about the y-axis this time. So in this case, v is going to be equal to pi times the integral from b to a, or from a to b I should say, of x squared, because it's about the y-axis, dy. Okay. So remember, it's just kind of the opposite variable. So if you're rotating it about the y-axis, it's x squared. If it's about the x-axis, then it's y squared. And obviously, this is just the opposite variable here. So, x squared, well, that's just going to be this squared. So, v is going to be equal to pi times the integral. So, let's just put our limits in. So, it's between 1 and b. So, we don't know what b is yet. That's what we're going to work out. X squared, so that's, you know, if you take this quotient here, if you square it, it's just the same as squaring the numerator, squaring the denominator separately. So 1 squared is 1. And then the denominator squared will just be 2y plus 1 all squared, right? So hopefully that's not too bad so far. dy. And again, at this stage here, substitution is a really nice way of tackling this integral. So using substitution. So using substitution here. So again, I'm going to do it in terms of u. So u is going to be equal to this here. So 2y plus 1. Okay. Again, let's work out du and then work out dy. So du by dy, that will just be equal to 2. So in other words, dy is equal to du divided by 2. Okay, so this should hopefully be quite a nice example. So let's just rewrite our integral here using our substitution. So v is equal to pi times this integral between 1 and b of 1 over u squared. Okay, so u is 2y plus 1, so this is 1 over u squared. Don't forget, we're replacing dy with du over 2. So du over 2. Or in other words, you could write that as a half du if you prefer. So I'm going to take this half out to the front here, again using linearity. So we can write that as pi over 2 times the integral from 1 to b of 1 over u squared du. Okay, and now we can work with this. Again, I'm just going to keep the limits the same here, and then just using my original limits. I won't transform or anything like that. So again, let's perform this integral here now. So this would be u to the minus 2, add 1 to the power divided by the new power. So it's pi over 2 times, so u to the minus 1, that would be u to the minus 1 if you add 1, and then divided by the new power, so it's going to be minus 1 over u to the 1, but this shouldn't be anything too tricky, just standard A-level integration, and then obviously my limits would be b and 1. Okay, once we substitute back our u. So that will be pi over 2 times minus 1 over 2i plus 1 between 1 and b. Okay, so if I take it over here, I'm kind of working too far to the right. So this is the result of the integral. So all I need to do here is sub this in, and we know this is equal to pi over 10. So again, if we just write this out, pi over 2 times the result of the integral between 1 and b. As we're told in the question, the volume of the solid generated is pi over 10. So pi over 10. Okay. So at this stage here now, we just want to start simplifying and just solving. Okay. Obviously, at first, let's just put in our limits. So if you put your limits in here, this is pi over 2. So put b in, you're going to get minus 1 over 2b plus 1. Like so. And if you put 1 in, say this is minus 1 over 2 times 1 plus 1. So that would be minus 1 over 3. But remember, this is minus 1 over 3, so it's plus 1 over 3, like such. Okay. This is equal to pi over 10. And now we can start solving here. So I think the first thing we can do is just times through by 2 here. So we're going to get pi times this here. Just write it that way, make it look a bit neater. This is equal to, so that'd be 2 pi over 10, pi over 5. And now I can divide both sides by pi. So that's going to give me just this here. If you if you divide this side by pi over 5, that's just going to leave you with 1 over 5. Okay, it's the same as doing pi over 5 times 1 over pi. So that's equal to a fifth. And now if we just start solving this, so we carry on up here. Let me just go to this first. Okay, let's carry on back at the top. If we just solve for this here, I'm going to take this onto this side, make it positive, and then subtract 1/5 off both sides. Like such. Work this out here. That's equal to 2 over 15. And then times through by the 2b plus 1, but again this should be pretty standard algebraic manipulation. Times that by 2 over 15, that's equal to 1. If you times through by 15 over 2 now, I get 2b plus 1 is equal to 15 over 2, and then just subtract 1 and divide by 2. So 2b is equal to 13 over 2. So therefore, b is equal to 13 over 4. Okay, so that's our upper limit. So like you can see, there's a lot of working going on for these questions. I have drawn out this last bit of work in here a bit. You know, if you're confident with just manipulating it, then just go straight through with that. You don't have to drag it out quite like I have, but just so you can see the working in full there, that gives us our value of b. So moving on to the final question here now. Let's see what we've got. So we've got review exercise 1 here, question 45. We've got a curve with this equation, y equals 3 sine x over 2. So 2 parts to it. First, just find the area of the shaded region, and then part B, we're going to find the volume of the solid. So let's have a look at part A here first. So if we just write it out, so we want to find this integral here, that will give us the area. So we're going between 0 to 2 pi, and we're integrating this here. So this is just a standard integral that you can work out, just a standard trig integral. So hopefully it shouldn't be too bad. So you're going to get 3 times minus 2. So if you think about what sine integrates to, you're going to get minus cos. And then obviously don't forget you're dividing by this half here. So I'll give you minus 2 there. Cos x over 2. Okay. Your limits are 0 and 2 pi. So just expanding, well, just working this out here. 3 times minus 2 is minus 6 cos x over 2. Between 0 and 2 pi. Sub your limits in here, see what you get. So what you're going to get here is 6 minus 6, which is obviously just 6 plus 6, giving us 12 there for the area. So that's just part A. So that was quite a nice 4 marks, so just to get us started. Part B, bit more work to it. Let's have a look at tackling it. So for part B here. So think of part A as just a bit of a warm-up. Same kind of principle in part B. We're going to be integrating. Obviously, we need the volume. So we're about the x-axis. So v is just simply pi times the integral from a to b of y squared this time, because it's about the x-axis. Okay. Now we know what y is. Y is just 3 sine x over 2. So y squared, that will just be 9 sine squared x over 2. Okay. So if we write that out, v is equal to pi times the integral from a to b, where a is 0 and then b is 2 pi. So from 0 to 2 pi of y squared, which we've already got here. Dx. Okay. Now this integral here at this point is quite tricky to work out. So just like we did with question 1, we want to use trig identities to make life easier. So one identity that we could use here, if we think about double angle formulas, we could write cos 2x as 1 minus 2 sine squared x, like such. So that means we can write sine squared x, because don't forget that's what we've got out here, sine squared x over 2. So sine squared x would be 1 minus cos 2x divided by 2. So now we could write this in terms of x over 2. So sine squared x over 2. That would just simply be 1 minus cos, so 2x divided by 2, just x divided by 2. Okay. So far, just getting basically our preparation here for this question. We can take this 9 out again using linearity. So v is equal to 9 pi of the integral from 0 to 2 pi. And if we replace this with our identity here, this is 1 minus cos x divided by 2 dx. Okay, and again you can take this 2 out, so if I do that actually, if I just erase it and then try that as 9 pi over 2 there. So 9 pi over 2 times the integral from 0 to 2 pi of 1 minus cos x. We've got a nice standard integral here now. So that's 9 pi over 2. If you integrate this, that'll just be x. Minus cos x, if you integrate that, we just get plus sine x there. Okay, between 0 and 2 pi. So at this point here now, all we need to do is plug our limits in. So 9 pi over 2, plug in 2 pi in, plug in 0 in here, and evaluating that, what we get is we get 2 pi. So what we've got here is 9 pi over 2 times 2 pi. So the 2's are just going to cancel here to give us 9 pi times pi, which just gives us 9 pi squared there for v. Okay, so like you can see, that's all the work in there for that one. So that brings us to the end of this video. We're going to go through parametric curves, and we're also going to go through modelling as well. So there'll be separate videos. But I hope this has helped. Any errors or anything like that, please just let me know down below.